Dean and Uma. Okay, so we started the recording. I'm the Students and Alumni Relations Officer, and I'll be facilitating the webinar today together with Tim, our Information Officer. So thank you so much for joining our webinar series on integrated circuits and devices research in the Philippines with the event titled Modular Open Source Analog IC Design. So this is in collaboration with IEEE and IEEE Solid State Circuit Society. So before we start, just a few reminders. First, always address everyone in courteous manner, especially later we'll be having our Q&A portion after all the talks. And also, please mute your microphone. So have your microphone unmute at all times unless acknowledged or you are called to speak. So it's since we're in a webinar type of presentation. So later, we can ask people who wants to. You can select the hands up reaction so that we can acknowledge and ask you to speak. And just a reminder that this meeting is being recorded and posted online for information dissemination purposes. Okay, so without further ado, let's all start with the national anthem.
Magiliw, pesta silanganan, alab ng puso, sa dibdib mo'y buhay. Lupang hinirang, tuyang ka ng magiting, sa manlulupig, di ka pasisilig, sa dagat at bundok, sa simoy at sa langit mong bugaw, may nilagang tula at awit sa paglaya minamahal. Ang kisap ng watawat mo'y tagumpay na nagdinigdig, ang bituin at araw ng kailan pa may di magdidilig. Lupa ng araw na walhati pagsinta, buhay ay langit sa piling mo. Sa piling mo, aming di kaya dapat ay mga api, ang mamatay ng dahil sa'yo.
Okay, so there's our national anthem in doxology. And for today, to share with you information about our speakers. So for our first speaker, we have Sir Ryan Albert Antonio. He's a junior faculty member in UP EEI He received his master's degree in electrical engineering and his bachelor's degree in computer engineering from the University of the Philippines, Diliman, in 2020 and 2016, respectively. He's also part of the Microelectronics and Microprocessors Laboratory. His current research interests are hardware architectures for hyperdimensional computing, hardware accelerators for machine learning, and asynchronous circuit designs. Together with Sir Ryan is also okay. So we also have Sir Lawrence Roman Quizon, a master student and teaching associate at the University of the Philippines, EEI. He received his bachelor's degree in computer engineering from UP in 2021 as magna cum laude. His research interests are primarily on resource-efficient AI accelerators, and neuromorphic computing. So let's all welcome Sir Ryan Albert and Sir Lawrence. Sir, good afternoon po.
All right. Thank you, Claude. Hello. Good afternoon, everyone. Lawrence, kindly prepare the slides. So I'm in the lab, so the internet might cut me off later, but just in case. I hope you guys are having a great afternoon, and thank you so much for attending this talk. Right. So just to give you an idea, this is more of a motivational talk rather than a technical talk. Right. That's because the technical stuff that we have prepared for you are all in a documented tutorial, which we'll be sharing for everyone later on. Okay. So the talk for today is about mosaic. So I'll go into a bit later on what in the words is mosaic thing, right? But essentially, what we're trying to do right now is that we want to revolutionize IC design. Okay. There are many practices that we have been doing ever since, for the past decades. But this time, there is something very peculiar about mosaic. Okay. And to start off with, let us try to set the grounds for the motivations of this talk. Right. Next slide, please, Lawrence. Okay, so as you can see, there are these challenges and needs for in IC design, right? First and foremost, we want to increase our productivity without the buyers of licensed software. I'll give you an example, right? When 2020 started, the height of the pandemic started, maybe for some universities, but especially here in UP, we've experienced limitations due to licensed software, right? That we are actually constraining our productivity, that we have to go to the lab, use the computers in our lab, because that's where the licensed software are. Sure, we can do it remotely, but then, when the license has expired, that becomes another problem, right? So essentially, what happens with our undergraduate students is that, the time that they can spend tinkering with the tools and learning how to do IC design was actually hindered because of these challenges, right? Now, here's the thing too. Um, we need to produce more hardware engineers who have confidence in IC design, right? Now, you see, I'm pretty sure that any engineer like you would be, you gain confidence once you know or you master something, right? And because, since again, going back to the idea that we are using licensed software, right, we're constraining our time and space in the laboratory only, but not in the comforts of our home or in the comforts of our free time, right? What if we're actually more productive maybe early in the morning or probably late night in the evening, right? So what happens there is, because since we're not practicing so much, when we graduate, some of us are not so confident in doing IC design. So what happens? Most of us go into software engineering. It's not a bad thing, but I mean, the point is that there are much less hardware engineers nowadays, all because of one of these things, right? And on top of that, if you're working in a company, right, analog design has this iterative and manual process. You do the GMID things, you do the layout. But what if we can actually automate this to again increase productivity and at the same time try to speed up our time to market for our products, right? And last but not the least, right? What if we can programmatically design analog modules for reproducibility? That means if you need IPs that you need to specify different gains and bandwidths, right? And then you can have it readily available for flexible parameters, right? Which actually adds a little bit more, or actually significantly more, for faster time to market. And that's a good thing for companies as well, right? So these are the challenges and the needs that we are trying to reach out for right now. So the solution is, next slide please, Lo, is this Mosaic modular open source analog IC design community. It's our revolutionary solution. Okay, this is something that was taught to us over last August by our friends in when we are actually in Austria. Okay, because this community that we're trying to develop really is to foster a bigger collaboration with the use of open source tools to take away the barriers for licenses and to advance the state of the art in analog IC design to make them programmatic. Okay. Now today, this is something that we'll be discussing, okay? And we'll be sharing to you everything that Lawrence and I have learned last August. Right. Now, just to give you a little bit of a hook or a cliffhanger of what we're trying to envision the future, right? Next slide, please, Lo. Okay. So the future of IC design and education is that we want to try to achieve two things. First and foremost is to have a uniform open source platforms, right? Uniform and open source because one, again, as mentioned earlier, we can take away the barriers of licensed software, and we want to make it uniform so that all the students from different universities can learn the same thing. Okay, it's not just here in UP. Okay, it's not just there and maybe in Mindanao State, Batangas State, so University of San Carlos, right? All of us are studying the same thing. Okay, now this can foster, it has easier inter-school collaboration. And then, every time when there's something that we can collaborate about, it actually increases our productivity, right? And first and foremost, we have a common ground of knowledge. Now imagine that there's no exclusivity that you can only learn things because you have licensed software or not, right? But all the things that you're learning in school is not restricted to your school itself, but instead it's scattered around the entire Philippines for that particular matter. Right. And second thing that we want to achieve really is this concept called the programmatic modular IC design. Not just analog, you see. It's also in a sense also including digital circuits. Why? Because one, we want to significantly shorten project lifetimes. If you're working in a company, the faster you can produce more products, the more money you can bring in, right? And that's how software companies do it. Because software companies, the project lifetimes are right what like 6 months to a year. But in hardware, especially in semiconductor companies, how long are projects? 3, 5, 10, depending on how long it is. Because hardware design is very, very meticulous and very, very difficult. Right. Now, last but not the least, for programmatic and modular IC design, what we want to do is that we want to make designs become more parameterizable, reusable, reproducible, and clear. Okay. One of the hurdles in maybe when you try to do IC design is that you have there's this learning curve when you're trying to study a new circuit. Like for example, young researchers like me and Lawrence, when you read the white paper, you don't necessarily understand it immediately, right? You have to spend time trying to tinker with it, and then in most cases, these white papers don't even tell you how they design their circuits. They just say, okay, circuit works, maybe just size it a little bit so that it operates at a certain region. But there is no clear definition on how you actually build this circuit, right? But what if there's a capability, which is a programmatic modular IC design to actually reproduce these things right off the bat from your circuits in your white papers, right? So this is all the motivation that we're going to experience or learn from us today. Okay. So next slide, please. Now. Okay. So basically, the overview of our talk is really two things that we have learned from our trip in Austria last August. Right. One is the essence of open source. Second is the concept of analog generators, which is I'm pretty sure will be very interesting for both universities and companies. Right. Challenges for this mosaic community. And we have a special guest who will come later, Dr. Mira. So she'll be saying a few words to all of us and probably invite you to something interesting. And also the starting of available resources that will be provided. Okay. So time check. Okay. Let's next slide please now. Okay, so the Mosaic Bootcamp, okay, last August, this year only, Lawrence and I had, thanks to Sir Louis and Dr. Mia, that we had the opportunity to go to Linz, Austria. Okay. And there, in the Mosaic Bootcamp, what we did was to collaborate and to study with a bunch of young students, as well as together with experts coming from different countries, from the Philippines, US, South Korea, Chile, Netherlands, Australia, oh, so many, right? And what we did here was really to understand, okay, why are we trying to go for open source and modular IC design, right? So that's the entire gist of our training. This lasted for 1 month, and for every week we had different talks, different sessions. We had different tutorials and workshops. It's one big boot camp. It was pretty fun. Okay, next slide, please. But let's first begin with what is open source, right? So some people have this what do you call this preconception of open source, that it's always something that is free. Technically, it is free, but the better definition would be it's a publicly available set of resources that can be modified and reshared to anyone, okay? Because it's a public resource, right? And these open source communities and open source projects, they still have licenses, right? But these licenses are usually things to protect their uh, the designs or whatever the development they're trying to do, right? But the nice thing about open source, as opposed to something that's not open source, is that we have open exchange, meaning anyone can jump in, right? We can teach those who are new. We can invite more experts to actually criticize and give us feedback with their work. Again, I'll keep repeating the word collaboration because it's the number one thing that this open source community is trying to achieve. We also have transparency. You can see all the changes, all the updates that are happening, okay? So that anything that you're also trying to develop, if you are aware of the changes that are happening with your base components, okay, or resources, you can also automatically include it in your designs, right? And last but not the least is this word called the meritocracy. So if you go to Google, what it really means is that open source communities or projects are governed by actual experts. So it's just not, anyone just jumps in right away. Okay? It is actually a systematic and organized community, okay, or projects for that matter. So just a side note that all of the discussions for what we're going to discuss here is coming from Boris Merwin's talk called The Democratizing IC Design. You can look it up on YouTube. It's actually in our YouTube page. But we'll share it with you guys later. Right? Next slide, please. Okay, so there are different types of open source, and I'm pretty sure some of you have seen of these already. For example, open source software, there's several of them right off on the internet. So basically what you're doing is that you share your source codes. You can use it for your own projects. The idea is that you don't need to build things from scratch, but instead, you get a piece of this, piece of that. That's what we do as software engineers, right? Or even people who know how to program. You get a piece of everything to put it into your project, and then blah, you have a bigger project. Okay. Now, the idea is to combine all of those small open source codes to make big ones. For example, in Boris Merman's talk, he demonstrated that, did you know that Microsoft PowerPoint actually consists of several open source programs or projects as well, right? A-Sprite, for video gamers out there, if you know drawing your sprite and sprite characters, A-Sprite is also open source. You can pay for it if you want to build it automatically, or you could just build it up on your own. Right. Another thing is about open source that we also have open source hardware, which is the idea is to share your source codes, which are basically schematics, blueprints, logic designs, and so on and so forth. But again, the idea is that these things can be studied, modified, and created for the community. Right. One good example is OpenBCI. You look it up on the internet. It's basically a open source hardware for brain computer interfaces. So they give you the circuits and all this other open source hardware for you to develop on your own. Okay, so you can look it up. So it's one example. Now, the third thing that we're trying to achieve, really, next slide, please, something what we call the open source IC design. Right. So what is open source IC design? Basically, it's to provide you the tools that you need for IC design. You need the tools that you can use to study, modify, create, or recreate, or distribute your IC designs. Okay. So all of this from simulators, schematic drawing tools, layout is important as well, and also the PDK, right? The packages, the technology packages that you're going to use. Because the idea is that we want to democratize, okay? We want to give everyone the equal opportunity that they can make their own chips. All right. So a little bit more on the motivation. Next slide, please, no? Okay. So again, I just like to peg into your mind. So why do we need open source IC design, right? So here's the reality, especially for companies, right? In software, they're making billions of money, right? And then, but if you look at how software companies do it, there's a chunk, like billions of dollars down there. Okay, the foundations of what they're doing is all coming from open source software. Okay, but they're able to present or give out products, open source software, not open source software products, but rather software products that can earn them billions as well. But if you move to hardware design, right? And I'm pretty sure companies will know this, that if you try to create a very complex SoC, a system on a chip, sometimes you get the processor from one company. Sometimes you get an ADC from another company, right? Sometimes you get the non-volatile memories from another company. Okay, and all of those cost money. So design costs are exploding, right? And on top of that, okay, there's another reality check here. So there are much more software designers out there rather than hardware designers. Why? Because hardware design is difficult and challenging. As mentioned earlier, right? Some of us don't really have the confidence when we're fresh undergraduates don't really have the confidence to do hardware design immediately. What do they do? People like me, we have to go to and take MS immediately, right, to get the experience, right? The other thing is that debugging is very difficult in hardware as opposed to software, right? Writing code, somewhere there, but in hardware it's much harder. Have you seen the net list for ng spice? Right? I mean, it's not that elegant in some way, right? But and then you have to read codes, somewhere there too. And most of all, the cost of bugs. If you have a bug in software, what do? They just patch your software and then it's good to go. In hardware, what do? If you find a bug in your system, you have this thing what they call is to respin your from the design to the verification and up to the fabrication, right? So you have to do this respin things, and they're very costly, and that's high cost in hardware, right? So the point is, heavy tasks are there in hardware, yet we have very few engineers and tools to help us solve these problems, right? So going on, next slide, please, Lo. Okay. So the idea, the solution really is to democratize IC design. It's a new movement, not for just for us in the university, but also for companies as well, right? Why? Because we'll give you benefits of what you're gonna see, right? I'll give you one. In the succeeding science, I'll show you examples what this open source movement is trying to achieve. Next slide, please, Lo. Okay. One good example is from Sir Louis' talk last week, right? The CIDR EE220 class. If you noticed, all right, so some of us may be taking master's classes, right? And then during my time when we were taking master classes under Sir Louis EE220, it was like around 10 to 20 students at the time, right? And it's exclusive to UP students only because we had the tool of cadence in our laboratory, right? And we're just discussing it here. But when Sir Louis opened his E220 class, and he's using open source softwares like ngSpice, XChem, and Magic, look what happened. The biggest thing that notice here is that we have 300, or rather, he has 308 participants, not only exclusive to UP, but also in different regions of the Philippines, right? And not only that, it's not just undergrads, not just grad students, but also engineers and other faculty members. So this itself is one step to getting closer to, hey, how do we actually make this open source uniform open source platform for everyone, right? Next slide, please, Lo. And then not only that, it's not only in the Philippines who's trying to make this movement, even in Chile. Our friends from the Universidad Técnica Federico Santa Maria, okay, these are Chilean friends that we have. They're also trying to create their own tutorials for open source tools, making it available for people to jump in right away. So you could check this out. We'll be providing the links later. Don't worry. Next slide, please, Lo. And another thing is that even big companies, right, are starting to jump into this train. Like for example, the Chips Alliance group. So Chips Alliance is the common hardware for interfaces, processors, and systems. And the idea is that they give you high quality open source hardware, okay, so that you can make your own chips right away, okay, or not necessarily make your own chips right away, but reduce the cost of the development of chips, okay. And then since it's an open community, anyone can give out ideas, and then you can learn from the experts. Okay? Check this out on Google. It's a very nice community right now. Next slide, please, Lo. And another thing, one of the initiatives to move everything to open source is that the most prestigious conference, SSCS, is actually providing the PICO program, which is the platform for IC design outreach. In a nutshell, it's a chipathon. So if software engineers have a hackathon, us hardware engineers have our own chipathon, wherein you can make your own circuit designs, submit it, and if you get and if the judges like your designs, you get a chance to have your chip fabricated for free. And the interesting thing about it is that you have to use open source tools. Okay, next slide, please, Lo. And just to give you a bit more ideas, in 2021, they submitted 61 designs. 18 of them were selected, and 11 of them were taped out, right? So it's a growing community, and it's coming from different countries as well. Okay, So in the Philippines, I hope one of us, especially for universities listening in right now, that you could look it up on the internet as a CSP program, and then you could try to think about, okay, maybe we could take a shot in this, right? And that would be really, really cool. And another thing, next slide, please, Lo. Um, just to give you an idea, what do these people, those 11 tape out projects, what did they ever tape out? Look at that. They have a 5G bidirectional amplifier, wireless power transfer unit, variable precision, oscillator based LVDT, temperature sensor, and so on and so forth. And these are interesting projects. They're not like, simple op amps or like that. They're actually systems that they're trying to tape out from different universities. Look at that. They're all universities. Now it would be great if the Philippines has, a shot in it too, not just from the Philippines, but I encourage other universities too around the Philippines, like Mindanao, Batangas, State University, San Carlos, and so on and so forth. Take a shot at this. Okay. So last but not last two things. So essentially the challenge for open source IC design is that it's actually a long-term investment. Okay, and it will take time, right? So it's not gonna, Rome was not built in a day. You will be, what do you call this? Roles that with a day, it will take time for this to develop, right? And one of the challenges that we're facing is that time, and we also have very few talents. But the thing is, we also have a growing community, which is good. So you could, uh, you can jump in right away. And the only step forward really is to prepare the future generation of talents and build this community for everyone. All right. Okay. Last but not the least, how do you get started really? Okay. Next slide, please. No. Okay, perfect. So how do you get started really? Sorry, we're not providing tutorials for these things because we provided tutorials for something much more interesting. But ngSpice, XK, Magic, K Layout, all these open source tools that were actually taught to us, right? You can actually find several resources out there in the internet right now, and everyone's really trying to get this thing going. Go to Sir Luis E220 class. We have that link later on, or some of you maybe have been attending it. That's a good example of having how to deal with or how to get started with these open source tools. Okay, so without further ado, that ends my part for open source tools. I'll entertain questions later. I'll pass the floor to Lawrence for the second part, very interesting part for our talk today. Thank you, Lawrence.
Okay. Thank you, Sir Ryan. Good afternoon, everyone. I'm Lawrence Quizon, an MS student at UP Microlab and CIDR under Project 3. So I am still a fresh graduate. I graduated last year, so I'm not no particular expert yet. So please bear with me. Uh, so for the part about the analog generator, analog generation rather, first I want to show this graph. This graph shows a common sentiment with respect to the design of chips. For the same chip, the required design effort for designing the analog portion bottlenecks the creation of chip designs. So we can attribute this to the amount of design effort required because design automation is vastly different from between digital and analog. So, for example, in the digital design, we can go straight from a desired behavior or specification into coding it behaviorally. We call this behavioral modeling. And then we use the tools that give us from that code, that is Verilog or HDL. And the tools give us a working circuit or layout. The thing is, automated digital design has far outpaced the development analog um, of analog automated design. And this is not because we lack any attempts or because we haven't tried. The thing is, people have actually looked at automated analog design for decades. So since the 1980s, people have tried to look for ways and tried to develop systems for which we can automate analog design. So the thing is, what's the holdup? Why could automated digital design have picked up so well and analog is lagging behind? So it feels like the reason is that in analog design, there's just so many more ways to get things wrong than to get things right. For digital, you have these extremely robust, noise-resilient CMOS blocks for which you only have to worry about delay problems, factors mostly external to the blocks themselves. For analog design, you often have to dig deeper into the blocks, replace topologies and whatnot if you cannot reach the desired specifications somehow. So then, if the problem is exacerbated by these constraints, why are we talking about it now? Well, in Mosaic, Mosaic tries to put forth a solution. So instead of trying to create a software one time, instead of trying to create something that generates everything that you may ever want, we need to do it step by step. So this is why we call the M in Mosaic modular. We need to do it in a modular manner. The idea is for some circuit that you want to design, you create it not by placing transistors into a schematic editor and then connecting the ports together with wires that you draw. You can instead do it by writing code that does it automatically for you. And so what does that change? You just went from a schematic editor to just typing on your keyboard. Well, coding languages like Python, for example, are optimized to be extremely modular and reusable. So then, if, for example, you have a loosely related specification, that is specification number 2 versus spec number 1, you can reuse parts of the code for spec number 1, even if it may have a different topology. So long as that code was written well and is sort of reusable, you can avoid doing the heavy, maybe not particularly novel work that you did the first time that you coded your design. And this is what in Mosaic we call the code-based design methodology. And what happens with this is that, okay, at first you might have a lot of trouble creating the first design, but as you create more and more designs with code-based methodology, each iteration of the software base gets more and more refined and more general, and it becomes more and more reusable every time, because you will find that someone has already made the changes that you code that to the code that you may have wanted. Of course, that is given that your code is made to be reusable to begin with. So I don't know about everyone else, but as an engineering undergraduate, I tended to ignore the more tedious parts of coding that are not really particularly needed for the functionality. That is putting things into an object-oriented manner and writing the doc strings. And that's a major difference. The code I had to submit in undergraduate classes and the code that I need to make nowadays are different, in that the latter needs to be more readable and usable by someone in the future, mostly me. So going back to analog generation though, before it would have looked something like this. You have requirements, you need an analog circuit. So you try out concepts, you try out designs, you do your equations, you try many different topologies, some of which fall short, and you eventually end up with something that works. So you start working on the layout, which you then later on verify for the correct functionality, and sometimes that doesn't work, so you go back to the concept and design. But for the future, what we can envision with the kind of code-based methodology that we're talking about, in maybe say 5 years of incremental effort or so, some IC designer will come up with specific requirements and walk away without having to write a single line of code. Now, that's going to happen far into the future. We know that that kind of wishful thinking does not end up well for when we try to make a one thing, one software does everything type of thing for analog design. But at some point, someone will come with specific requirements that are very closely related to something that someone has done before, and they walk away without having to write any single line of code. Because someone else's work has, by incremental contribution, ended up creating enough reusable code to cover everything that that designer needed. And then a few more years after that, most people will only be writing very few lines of code, mostly using code that people have made before to systematically create the needed submodules. So one of the other sub benefits of this is because the PDK comes in as a process between the code and the layout. So therefore, when you write in a code-based design methodology manner, you don't have to think about what the specific process node for your design is, so long as, of course, someone has already made the software pairing the specific process to the code. Of course, also paired with some systematic design methodologies. And this pairing of the process to the software only has to be done once. Of course, after it has been done once, someone may encounter bugs along the way, which it has to be done again. But that's something that we live with, and that's something that also software lives with as well. But from that, we can enjoy some benefits. So in the usual full custom development timeline, the company makes the initial design right here. And from there, they try to move to another process node, which breaks everything. They try to fix it and end up with the first derivative. And then they move yet to another process node. Everything breaks yet again. They fix it and end up with the second derivative. Now, with code-based analog generation, the first design will have a lot of coding overhead, more so than if it was designed manually. But given the existing code augmented with a systematic design methodology and well documented, it may be possible to avoid tedious and repetitive parts of the design, saving a lot of time when we move process nodes. So here is an example that Ayan this was a PhD student from the Berkeley Wireless Research Center and the current head developer of Bag 3, showed us as a benefit of using Bag 3 for his layout generation. Of course, as we expected, the first instance of the code-based design takes longer to make than if it was designed manually. However, any required changes in the design, like here, the size of the antenna, takes literally the change of one parameter in the code. If it had been done manually, the entire layout would have to be changed, as the dummies would have to be moved around, and you'd have to redraw with your paint tools the antenna itself. So that's it. The major challenge to doing this type of code-based analog design methodology is trying to create code that is reusable and well documented. A lack of this has for a long time kept the entry hurdle high for anyone wanting to try out the existing software. And so in the end, what the Mosaic community thinks is that we need a new generation of IC designers. And it will probably come from the literally new generation, fresh undergraduates, master students, because as the newest generation of IC designers, we are digital natives familiar with coding, yet we are IC designers by profession. The new generation thus ends up with exactly the skill set that is needed to become a code-based analog IC designer. We were trained to have the hardware skills, and also through exposure and some instruction, we also have the software skills. Now, I mentioned something in this slide. I mentioned that the entry hurdle remains high. Now, that is true, it does, but it's not as high as it used to be. Since the Mosaic Bootcamp, the community has realized that there has to be an emphasis on making these things accessible to its users, hence the emphasis on using open source. And that realization has also led to the creation of easier processes for installment of the said software. So now we would like to present to you some of the software that we have made to be in arm's reach. First off, we'd like to introduce you all to Layout with Gridded Objects, LEGO, developed by Hanya University's Nifty Chips Laboratory. You can check it out by going through the link here in this slide or just Googling Lego 2 because they'll be the first result you see in Google. Basically, as it is, Lego 2 is a layout generator. It reads Python code and it generates a layout. But not just that, it is one of the things we want to show you because it works with fully open source tools. This layout is of Skywater 130 PDK, and it is shown in Magic VLSI, which is also open source. Now, the friends from Nifty Chips Lab have used it for multiple tape outs, though not necessarily with the Sky 130 nanometer PTK. But on the other hand, we can take from that the fact that Lego 2 is compatible with more than one PDK at the moment. Just with some and with any sort of PDK, just with some initial coding overhead and some drawing overhead. So in a nutshell, Lego 2 is Python code that generates a set of tickle commands, which the Magic VLSI layout tool can then read step by step in order to draw the layout. Now, what's great about Lego 2 is it's very easy to start using it. So if you're interested, I have made a tutorial and linked it in the CIDR website's page for Mosaic. This tutorial includes the installation process. You can go check it out yourself, but basically it makes it so that you have to perform relatively fewer installation steps to try to start generating layouts. Now, what about the future of Lego 2? Well, as of right now, updates are still regularly rolled out for it. Support for K-Layout instead of Magic is also being worked on. The great thing about this is it's already completely open source. All of the tools used are open source. And so if you have the time, the Mosaic community will greatly appreciate it if you could try to use it, test it, suggest some features, or maybe even fork and contribute to the code. The other analog generation framework we'd like to talk about is analog base. This is known as the Berkeley Analog Generator, developed in, you guessed it, UC Berkeley. Analog base is actually the core class inside the Berkeley Analog Generator code, which allows us to generate modular cells in which to place transistors. So shown here is a schematic of such a thing. So an example is here of an analog-based cell. So the gate widths of this design are different for the 4 rows that are present in this design. However, the gate lengths for this entire cell are all the same. And that's the constraint that we work with when using analog base. So analog base uses the BAG2 software in order to translate your Python code into a Cadence Virtuoso layout. It takes pre-made design templates, which are made in Cadence, ideally by someone before you, since it sometimes only has to be done once. But ideally, really, the only thing that you need to code is the design scripts in which you specify the locations and the connections between the transistors that you have in a single analog-based cell. The routine is very simple. You can go check it out in the analog-based tutorial that Ryan made in the Mosaic page in the CIDR website as well. But the scripts pretty much look like this. Ideally, the parameter setup script is already taken care of, and you only need to trouble yourself with the main layout script. So let's move on and see some examples of it in action. So here's an inverter that Ryan made using an analog-based instance. There are 4 rows on it. The second row is for the PMOS, and the third row is for the NMOS, and the last row, well, there is also a last row which is filled with dummies. Here are also the flip-flops that Ryan has made with the number of fingers easily changeable by tweaking a parameter. So here we only wanted to show what we ourselves have been able to make with the software. So it's very suspiciously digital. Rest assured though, analog base has been used to create much more complicated analog circuits like SAR ADCs. I have used it to make a stable voltage reference as well, though I lost that code. Analog base currently works with already several different PDKs. From starting from Berkeley, its use went and spread to everyone who then made it compatible with each of their own PDKs. Currently, the community is developing, and actually, this is one of the priorities. The community is developing analog base that works with Sky 130, XChem, and K layout. So in other words, that means that work is underway to make analog base completely open, work with completely open source tool flow. So like before, if you all are interested, it would be very helpful if you join the community to help out, test, suggest, and code. So Mosaic is the community that we'd like to be the umbrella connecting all of these projects. So actually, Mosaic has a GitLab repo that contains all of the related projects at the moment. In terms of the integration of open source tools, even without analog generation, we feel like the next step is curriculum integration. So Professor Louis' analog IC design class held for CIDR already uses OS tools in it. So this is a really, and I feel like that's a really, really important step forward. So at the end of Ryan's open source part of the talk as well, he mentioned something like this, which is actually a quote from Boris Merman, that the change to using open source tools won't be rapid, but the same did not happen overnight for software. So even though that's all great, the stuff that we have now are still maintained by a very small set of developers and also very few users. The thing that Mosaic needs the most right now are users. So if you're interested, it would be really helpful if you could go check out the Mosaic page in the CIDR website and go look at the short tutorials or the linked repositories that you are interested in. The Mosaic community needs both software and hardware skills in varying degrees. And as I've mentioned before, that is found in the newest generation of talent. So if you are all interested, please do come check it out. So thank you, everyone. Back to you, Ryan.
All right, perfect. Thank you, Lawrence. That's very nice and fantastic. Okay, so right now we have our closing remarks before we end our talk, and we'd like to invite Dr. Mira. She was our mom when we were in Austria, and she took care of us really, really well, and she made sure that we learned a lot. Okay, she's a big proponent of open source as a way to bring IC design closer to young people like me and Lawrence, and to bring new skills, right? So she's one of the people who's trying to make this movement really, she's trying to make this movement, push through. Dr. Mira, are you there?
Yes, I'm here. I joined the call.
Hey,
And
perfect. You can share screen.
yeah, I'm
Mhm.
trying to I'm usually using another tool. Yeah, I will stop. Okay. So I hope, please let me know if you can
We can
see
see it.
my, yeah, okay. So thank you so much for inviting me to this talk. I'm super proud to be here, especially as I'm a very big proponent of the open source, but also I would like to tell you a bit story about the Mosaic, how it all started, and what are we doing, and also bring some news regarding the potential internships that let's say I managed to secure. So basically a bit more than a year ago, I started looking into, and I got a bit more, let's say, freedom to communicate with other, let's say, competing parties. And we all noticed that we definitely need to collaborate to bring this new design methodology to life. And you can see a lot of people are kind of joining our Monday calls. We do it once per, let's say, 3 to 4 times per month. where we mostly discuss about, our progress. We try to team up. And, I also gave a talk oops, for some reason, I'm a bit slow. Last September during ESTRIC, which is a big, let's say, IC design conference here in Europe, about mosaic and what are we aiming for. So I come from a former communist country, and my vision is more like that education should be available to everybody, no matter no matter whether they're coming from this or that country. So what I always say is that let's say maybe the wealth is focused and concentrated in different parts of the world, but IQ is not. And we need to provide an opportunity to other people also to choose what they want to do in life. And since IC design has been considered a dark magic, like that is only available to a couple of people, I'm strictly and very against it. And that's the reason why I'm like very passionate about this topic. So what I would like to see is that we democratize IC design. And one of the topics that I'm very much interested in is basically open source curriculum. It's not just that you have open source tools, but basically you have a curriculum that is open. It uses open source PDK, open source tools, and it's also the knowledge available to people. And I believe that this Philippine initiative is actually going into that direction. That's why I'm very, as I said, very proud to be here. I also use my contacts to constantly inform people about what you're doing. So as of October, I'm part of Infineon, and I'm sending at least links to my colleagues. Of course, they might not be interested so much, but I want to make them aware that the world around them is changing, especially the world outside the companies is changing and becoming more open, more collaborative. I also, as you can see, I also border my contacts. So Tim Ansel is the main, let's say, the leading or like the main figure in this Google initiative. So I also make sure that I make other people who are like stakeholders aware that there is something happening in Philippines. So as what I would like to see, and I think also my colleagues who are part of Mosaic, is that we have active and vibrant open source communities where the new skills are built faster and new design methodologies built and tested in an agile manner. So the strategy, since we are all so different, everybody are having their own, but my strategy is lead by example. So I'm not a big proponent of PowerPoints. I'm a big proponent of scripts and hands-on activities, and that's the reason why we organized a boot camp where the main focus was on onboarding. And because I was talking at that time with so many people, we as a sidekick organized some let's say calls, presentations, such that the people who are present get a current update, of where this line of work is at this point. So at this moment, within Mosaic, we have several activities that are ongoing. Hopefully, at one point, we will converge and make, with these activities, one very strong, let's say, a framework. So at this moment, Virtuoso template, like our colleagues Marco Kosunen and Martin Köhler are working on it, where we use proprietary tools and let's say generic PDK from Cadence. What you need to be aware that, like in Mosaic, our institutions and our members are high flyers, which means most of them, if they cannot publish at RFIC and ISSCC, they usually don't bother. So that's why I see that that they understand that the importance of building open sources, community and scripts is super important. So they, besides this, like, let's say, daily job, they find time to invest into Mosaic activities. And I really am very, very, let's say, glad that I see this kind of movement. Besides this Virtuoso template that is, as I said, completely proprietary, but the framework is open source, but you need to use proprietary pieces. What we are also, like our colleagues Matthias Köfelein and Thomas Perry are working on, is basically to create the parallel reality, completely open source, with open source PDK, with open source tools. there we will need your help. It's not that you're going to develop something, but we need people to test it, to make it really, with one, let's say, with with the press of a key, out of the box, really a solution that will help people to focus on actually generate a methodology, not so much on the tools and the, solving the bugs in the framework itself. We have also an orchestrator that Infineon is kind of developing and working on it. You also have heard about the Lego 2. There is from Nifty Labs, Cascode Labs, Curtis Mayberry from Skyworks is working on it. In the SDK system development kit, Marco Cosone is working on it. I provided a couple of links on the last slide, so you can have a look at it. And if you are interested, contact directly people who I already mentioned. It's very easy how to find them. They're all members of this MOSAIC group. So I also came, because what I also want to show you is about the opportunities that Infineon starting to offer. And the first one that I managed to get approved is development of low-level IPs. Which means, for now, what I've seen that, the IPs have been developed as a big blob of code, and that is very difficult to extend and reuse. And what we propose is a bottom-up approach where you develop the small IPs and then you test them and you, continue to develop them by building a bit more complex circuits. And this is, the level of, what is the background that you would definitely need in order to make this success. This could be a master topic, this could be an internship. It depends, what you're after. Then the second one is the orchestrator, demonstrator that Infineon is let's say, interested in. And basically that is building, we need a demonstrator to demonstrate that basically orchestrator is able to take off some levels of complexity from the generators and also from the developer, to take over, a task like, handling the databases or going through some pieces of design flow, etc. And, for us, of course, there are three opportunities: either to do it for Virtuoso template or open source template over internal Infineon flow. We're okay with anything because, we want this to be brought, to the community. And here it is a bit more computer science profile, but as I said, it depends what your forte is, what you're after. These are the useful links. And as I said, I believe, out of all these topics, what I would like really to see and where we need the most help for testing is this open source VB template. If you have, any interest, please let me know, or Ryan or Lawrence, and we can schedule a meeting with Matthias and Thomas to show you what we have and how you might help. Yeah, this is everything that I prepared for today. Thank you so much for your invitation.
Thank you so much, Dr. Mira. That was fantastic. Okay. So guys, especially those in the university, Dr. Mira is hinting that they're offering internships, their company. So it would be a good opportunity for everyone, not just in UP, That's why we have the CIDR program open to all universities, because we want to distribute these opportunities around the Philippines. Okay. We are an archipelago. So the more, the more opportunities out there, you have to share it to everyone.
Yes. I just wanted to mention one more thing. So I know that, let's say, maybe University of Tilman or other universities have some possibilities for exchange and supporting the exchange of students. So that's why I'm looking also from Infineon for the opportunities to establish officially the collaboration, at least something with the university, such that for students it will be easier to let's say, use these opportunities. So at this moment, I'm I throw the ball to our colleagues in Singapore who are also working with the same methodology, such that they also check, because Singapore is much closer to you and maybe it's easier considering the costs and everything to let's say, to reach to go to Singapore than to come to Austria. But as I said, I will be from this side trying to support, also the university network spreading from Infineon side. Yeah. Sorry, I had to add this piece on. Thanks.
Yeah, super. No worries, Dr. Mia. Thank you so much for these opportunities. Okay. Lawrence, let's try to wrap it up already, I guess. The last few slides, if you could share your screen. Actually, what we're gonna do right now is to, oops. Oh yes, okay. So the last part is that we're gonna provide you the available resources down here. So hold on, let me put it in the chat box. Yep. So this thing I put in the chat box is the same thing that you're seeing in this slide. You can go to them, watch the tutorials, watch the YouTube channel. Actually, Lawrence says I would like to recommend you go to Mosaic YouTube channel. It's a little bit wrong spelling there. Swap the letters a bit, but that's essentially what we're gonna see. There is all the things that we have learned during our bootcamp with Dr. Mira last time. Okay. Next slide, please. Actually, that's the last. Thank you for your time and listening, and we'll actually open the floor for questions. I think there are questions in the chat box. Hold on.
Yes,
Actually,
sir.
Dr. Mira is typing an
Okay,
answer to one
Dr.
of them.
Mira is typing. Let's try to answer the others first. Please share the link shown in the slides. It's here. We showed it. Someone said, awesome. Thank you. No more questions. Okay. Any other questions?
Yes, I think for all the participants, if you still have questions, you may use the Q&A box, like the other participants are doing, and then so that Sir Ryan and Sir Lawrence can answer those.
No questions?
I guess maybe we should have saved one of the written questions to answer live.
Okay, there's a question. On our Facebook page, I think we don't have questions for the moment.
Okay, if you guys have no questions, hold on. Give me a sec. I'll upload the slides. Oh, we'll just share the slides and video recording in the CIDR-MOSAIC page, Ma'am Tata said. Okay. Yeah, we'll do that instead. Okay. We'll upload our slides and probably Dr. Mira's slides as well. So that you can look it up, and then the video too. Okay. Any other questions? Yes, you
Okay.
have the copy. Oh, suddenly there are questions. Hold on. Let's go with Eugene first. Can you give some examples on how long it took to develop some modules on code versus on schematics? Lawrence, would you like to take this?
Okay. Hello. So this one, we only have the say specific case that Ayan mentioned when he was talking about bag 3. You can find the video in the Mosaic YouTube channel. But the thing about this is he did say that it took a week for him to it took 2 weeks for him to write the generator based code for that RF front end, but the thing is manually it took 1 week, though edits on the manually designed module took an entire day, while the generated methodology took around 30 seconds for him to edit. Now, if we take that in mind, then you can see that it still took 8 days for the manual design to be completed, but it took 2 minutes plus 2 weeks plus 30 seconds for the code-based methodology to actually complete. Though the thing is, that is one particular example. He himself says that that for him, the code-based methodology works best for things like SAR ADCs for him personally. Now, the thing is, we don't really have too many examples of direct comparisons like that, because sometimes the thing is, when you make the code, you don't exactly make the same exact circuit manually for an experiment when they try to do things like this. So maybe that's something that that's something that the community might want to show for when we're trying to defend this methodology.
Okay, perfect. Thanks, Lo. I hope that answers your question, Eugene. Okay. There's another question here, but I think Dr. Mira is answering it. Okay, she answered it.
Yeah, I
Right?
wanted to just add some comments regarding, how much time do you need with this or that approach? Yeah, initially, of course, you need more time because initially you need more time if you first time see some circuit. Why? Because you need to figure it out. What are the trade-offs? What is what is the what is the flow that you and steps that you need to script, and for that you need to do it first manually, and that means that you for sure will initially have will need more time. So, and that's the reason why we're focusing on the blocks at the moment that are very much reusable, like LDO, band gap, some oscillators, or like ADCs, because we know that we will use them in the future. So why I'm saying this, because yeah, initially you need, let's say, at least double time or more. We calculated that you need to use them 4 to 5 times to kind of pay off. And in that sense, that is also, you cannot use it straight away from out of the box, the whole like script. Every time you get some new request, you need to bit retune it. So, but it won't be, starting from the zero. So what we believe that, especially in a big organization as like Infineon or Intel, that will pay off eventually. However, as said before, even without open source, with open source, it will take time. And yeah, hope I added a bit more information to this question.
That's perfect, Dr. Mia. Thank you. Okay, anyone else? More questions?
Sir
Email
Ryan.
questions?
Sir
Yes.
Ryan, I think we have a question from our Facebook page. Let
Okay.
me read it to you. Is there a way to automate transistor sizing? The sizing of width and length really plays a role on meeting the target specifications.
Okay. That's a very good question. Hold on. Let me think about it. There is a.
Maybe can
Okay.
I take over this, Ryan? Yeah.
Okay. Sure. Sure. Dr.
Yeah, I'm really sorry. Maybe I'm jumping in, but I know straight ahead what needs to be. So yes, there is a way and there is a procedure in back to and in other, like, of course, you have done it everywhere already with MATLAB, because there was like direct connection between the MATLAB and the Cadence. But now we are doing it also within the back. Either 2 or 3, does not matter. At the moment, Virtuoso template only supports layout synthesis, but somebody asked, if there is DRC or whatever, we are working towards that we clean layout synthesis, and then we put also the sizing scripts for some initial circuits, so, as an examples. And that will be hopefully next year, put also like open. As I said, in the original back to fork, you have it already. If somebody is interested, you can contact me. I can point you out where these like data is. So you're right. Yeah, this is another side of the coin. It is possible, and as I said, it is in back to fork, in back to like original, but it's not in this fork that we're developing and maintaining.
Thank you, Ma'am Mira. Thank you, Sir Ryan. I think
Okay.
those are the questions so far. The question we have from the Facebook page. Okay.
There's another question. Uh, Hold on. Let me read
Okay.
here.
So yeah. I think the attendee is asking which Facebook page. So actually, we're live
three, because back three is much more functional than back two. And right now, BWC or
Yep. Thanks, Lawrence. Uh, or I think you're in mute, Lawrence. Did you mute yourself? Oops.
Yes,
Oh yeah.
I'm muted.
I thought you were saying something. Okay. Anyway, in the interest of time, we'll probably answer this last question. I don't know why it's addressed to me, but you've talked about software versus hardware when designing. There are millions of programmers for software and just 1,000 for hardware when it comes to debugging, writing, and reading code, and the cost of bugs. It would seem that being a hardware designer would be more difficult compared to being a software designer. My question would be, and with all due respect, why should one consider being a hardware designer, and what are the opportunities that come along with it? Thank you. Okay, that's a very good question. That made me think. Let me think for like 3 seconds. I may not have the best answer right now, but okay. So, mm, uh, at the top of my mind, the only thing, two things. Okay, one, hardware design is very very interesting as compared to software design. To be honest, because yeah, sure, it's cool. You can make programs, you can make things in software, but you cannot make interfaces in software. Right. For example, how do you interface the analog world with the digital world? That's a hardware design. You don't do that in software, right? And imagine, I'll give you another example. What if maybe in the far future, just in case, all right, that all of us will be using neural sensors, well, neural links, something that you wear on your head, and then you can control your computer. Let's say a neural keyboard for that matter. Okay, wherein you're going to think about what you want to type or code into your program, but you're not using a keyboard, but instead you're just thinking about it. That's a hardware job. That's not a software thing. Well, I would say it's software hardware, yeah, but the starting point would be in hardware. Okay. So there are things that you can do in software, and there are especially things that you can do in hardware only. Okay. Interfacing the analog to digital world is one. Okay. That's why it's always I would suggest it's good to consider being a hardware designer. Okay. And yes, it is true that hardware design is difficult. It is challenging because it has a very tedious and meticulous process. But the benefits or the rewards that you get at the end of it would be, you know, it's something that you don't find just when you do software projects. Software projects are usually fast, small and fast. Hardware are usually big and slow, but there's a lot of things in it. Okay, so that's what I think of at the top of my head. That there are special things that you can do being a hardware engineer rather than a software engineer. Okay, so don't quote on me that I don't like software. I do like software. That's why you do software to make hardware, things like that. But there are just several things that you can do in hardware that software can't do also. Okay, I hope that answers your question. I think
From
Lawrence is also laughing. Yeah.
from that answer, Sir Ryan, it feels like so you said that parang it's probably partly passion, but also something that that had been talked about in a talk during the Mosaic bootcamp is the fact that you know not everyone can be like not everyone can be software engineers, because if we're all software engineers, who is there? What hardware is there to run the software? And the thing is that with how the world works, everything will eventually like there will eventually be compensation for people. As we know right now, probably the current events is there is something like a shortage of hardware engineers compared to software engineers at the moment, right? So um, it might eventually catch up is something that I'd like to add with that, aside from the passion thing.
Hey
Great.
Ryan,
Yes, sir.
so actually just that is very interesting question, right? Hardware versus software. But I think in the end, right, they're pretty much complementary. There are some problems that you would like to solve with hardware, and there are some problems that you would like to solve with software. Well, actually not even like, right? There's some problems that are easier to solve in hardware or even optimal. You can solve them optimally in hardware or in software or a combination of both, right? So it's not really a question of, is it hardware versus software? It's really about trying to understand both domains and using the best possible approach to solve a problem. And right, so it's really sometimes we'll see there's probably going to be somewhat of a merging at some point, right? So it's the same thing with what happens in digital, right? So now you can just write HDL and build the processor. Uh, and there's sort of this merging of concepts, right? So it's going to be really about making sure that we have enough people with enough skills to actually address the problems correctly. So that's what I think there. Thanks.
Thanks, Sir Louis. That's actually the best answer, I guess. That there are some things that you can do in hardware and some things you can do in software. It depends on the problem you're trying to solve. Okay. In the interest of time, thank you for attending. And if you have further questions, we hold on, who's this? You can actually email us instead. Okay? And yeah, that's pretty much it. Thank you for attending our talk.
Okay, thank you so much, Sir
Wait,
Ryan.
can I
Oh, sorry. Yeah.
can I have something? So are there any other PDKs that from known fabs that support this mosaic paradigm? So if you guys go to the mosaic YouTube channel and find the second video over there, which is democratizing IC design by talked by Boris Merman, he did mention that Global Foundries, I think, is going to be releasing their 180 nanometer EDK, and Skywater is also soon to release their 90 nanometer as well. So yeah, that's that. And sorry po.
Okay, thank you so much, Dr. Mira, Sir Lawrence, and Sir Ryan. And thank you for all the attendees. Wow, we're over 170 attendees today. So thank you so much for your time and for joining us in this webinar. Thank you. And then we'll just share the recording of the webinar. Thank you, everyone. Have a great day.
Thank you
Okay.
and bye.
Bye.
Thank you. Yeah.